In this video, we're going to talk about the enthalpy of formation for a reaction. Every substance takes energy to break its bonds and it releases energy to form its bonds. So the energy change that accompanies the formation of 1 mole of its substance from its elements is called its standard enthalpy of formation. The symbol's kind of goofy. It's got a delta H for change in enthalpy. The little F stands for formation, meaning we're making that substance. And then the degree sign means it's all done under standard conditions, like 1 atmosphere of pressure, standard lab temperature. If it's aqueous, it would be 1 molar concentration. You can look up enthalpies of formation of several different substances. It could be presented to you as a chart. Oftentimes, if it's a problem that they're asking you to work on, they'll give you the enthalpies of formation of several of the substances, and then maybe have you calculate the enthalpy change for a reaction. The note at the bottom says elements have to be in their standard state of 25 Celsius, 1 atmosphere of pressure, and 1 molar concentration. When you're asked a question about enthalpy of formation, they're usually going to provide several different enthalpies of formation, but they might not include lone elements or diatomic molecules. If it's a lone element, it's already in its elemental state. So the enthalpy of formation, the energy that's required to make that, is 0. It's already in its state. So, for example, Cu, copper alone, or Fe, iron alone, or Na or Ne, those would all have enthalpies of formation equal to 0 because they're already in the state. Their elemental state is already what's presented. Same thing with diatomic molecules. Their enthalpies of formation would be equal to 0 as well, because there's no simpler form of hydrogen than H2, of oxygen than O2, and so on. You remember the Hofbrinkel elements, I'm sure. To get the enthalpy change for a reaction at standard conditions, we simply add together all of the reactant enthalpies of formation and subtract them from the sum total of the product enthalpies of formation. Now I'm going to show you a formula that looks really intimidating, but once we work a couple of sample problems, it'll become a lot clearer. So here's what it looks like. A lot of symbols. Delta H with the degree sign means the standard enthalpy change for a reaction. Then let's look at the first set of parentheses. This Greek letter sigma means add together. You may have seen that in math class. The letter N means you're going to take into account whatever the coefficient for each of the substances is and multiply it by the enthalpy of formation. And then the subscript product means take care of all the products and add them together. Do the same thing for the reactants in the other set of parentheses, and you're going to subtract the product total minus the reactant total. Let's walk through a sample problem together. Let's say we're asked to calculate the enthalpy change for this reaction given these enthalpies of formation. Our reactants are CH4 and O2. Our products are CO2 and H2O. Here's the basic strategy. To tackle this problem, we'll need to, 1, add up the enthalpies of formation of all the products. 2, add up the enthalpies of formation of all the reactants. And then 3rd, subtract the reactant total from the product total. Let's do each of those steps in turn. The products are CO2 and H2O in liquid form, but H2O in gaseous form has a different enthalpy of formation. And they gave us below the problem. You don't need to like memorize these or derive them in any way. They'll just give them to you. The enthalpy of formation for CO2 is negative 394 kilojoules per mole, and for water, negative 286. We need to find the sum of the enthalpies of formation times the coefficient for all of the products. So that means CO2, the negative 394, plus 2 times the negative 286 for water. The reason there's a 2 times is because the coefficient for water was a 2 in the equation. And if you add that together on a calculator, you would get negative 966 kilojoules. That's the sum of the enthalpies of formation for all of the products. Let's do the same thing for the reactants. The reactants are CH4 and 2 molecules of O2. They gave us the enthalpy of formation for CH4 as negative 75. And they didn't need to give this to us, but they did anyway. They listed it. The enthalpy of formation for O2 is 0. If you ever see a diatomic molecule or a lone atom, it's going to have an enthalpy of formation of 0. You need to know that because they're not always going to give that to you. Okay, so we're going to add together the enthalpies of formation for all of the reactants times their coefficients. In this case, it's going to be a negative 75 plus 2 times 0. And you might say, well, why do we have to multiply the 2? The coefficient is 2 in front of O2. And yes, 2 times 0 is still 0, but it's important to follow the format. The diatomic molecules, as I mentioned, are already in their elemental state. So they're going to have that diatomic molecule, that enthalpy of formation of 0. After adding up all of the enthalpies of formation for reactants, we get negative 75. The third step, subtract the reactant total from the product total. Our product total was negative 966. Our reactant total was negative 75. Here's that scary looking formula again. So we're going to take negative 966 minus a negative 75. From math class, you might remember when you subtract a negative, you're adding. So negative 966 plus 75 gives us a final answer of negative 891 kilojoules. Here's a way to represent that pictorially. We started with CH4 and O2. The energy required to break the bonds of CH4 was 75 kilojoules. So that amount of energy needs to be subtracted. The amount of energy required to get from oxygen to oxygen, 0. It's already in its elemental state. In the middle picture, we've got all of the atoms in their elemental state. And then in the picture on the right, we're forming the products. We're going to take some oxygen and a carbon to make CO2. And the formation of a compound from its elements always releases energy. So there's negative signs, meaning exothermic. Exothermic reactions have delta H's of 0, or of negative delta H's. And to form the water, we've got hydrogen and some oxygen. And we get, because there's 2 of them, negative 572. So if you add this all up, you get the negative 966 for the reactants. And we're subtracting from that the enthalpy required to break the reactant bonds. Let's tackle a problem together from scratch without the step-by-step part. This is one that would look like your homework. Find delta H for the following reaction using the enthalpies of formation listed below. Now notice this is a pretty big equation. We've got 3 reactants and we've got 2 products. So there's a lot to think about here. First, let's write the scary formula. The standard enthalpy change for this reaction can be found by adding together the number of moles times the enthalpy of formation of all the products. And we'll subtract the sum of the enthalpies of formation times the number of moles for all of the reactants. So our products are HCN, and there's 2 of them. Note the coefficient 2. And I'm going to pull the number 131.5 from the table of enthalpies of formation that they give us. And we're going to add together. That symbol sigma means add together. We have, as the other product, 6 gaseous H2O. That coefficient needs to multiply the enthalpy of formation. Now for the reactants, we've got 3 reactants to consider. We've got 2NH3 with an enthalpy of formation of -80. Plus, there's 3 oxygens. So I'm going to reflect the coefficient in the calculation here. And then I'm scanning the listed enthalpies of formation in the box, and I don't see oxygen. Uh-oh, did they not give us enough information? No, or they gave us plenty of information. Students, if it's a diatomic molecule, you put a 0. And then the third reactant, CH4, there's a coefficient 2, and then we'll plug in that -75. So here's our setup. Now it's time to do some math. Pull out your calculator. Take 2 times 131.5. And that gives us 263. 6 times -242. That's -1,452. 2 times -80. That's -160. 3 times 0, that's 0. And 2 times -75, that's -150. Then we'll add together the numbers in the parentheses. 263 plus -1,452, that's -1,189. And then the other set of parentheses, -160 plus 0 plus -150, that's -310. And then lastly, we'll take what's in the first set of parentheses, -1,189 minus a -310. That really means add 310. And our final answer works out to be -879 kilojoules. It's a lot of work. It's a lot of accounting, but the math certainly isn't hard. It's just multiplying through and keeping track of things. Good luck with the homework.